In this rather quick set of videos, we're going to be going over graph theory, which you hopefully learned in Foundations 1, and we're just going to be reminding you of the definitions and how we worked with graphs. To begin with, we have the definition of a graph. A graph is a set of vertices, V, and a set of edges, E. The vertices correspond to the nodes or vertices in the graph, and the edges correspond to the connections between those vertices. We've been working with trees for a while now. A graph is a generalization of a tree. There's a couple of useful notations we may see as we're going. The first is we can denote the sizes of these sets as the cardinality of them, the absolute value bars around the sets. We can denote the actual sets if we have a graph G by doing G.V and G.E. We'll use this notation in our code. To denote an edge, we write it as a tuple, Vi, Vj, and those are the two endpoints of the edge, the two vertices it connects. And the last thing I will mention is that edge, a bit of terminology, is that it is incident on edge Vi, Vj. So the vertices are incident on the edge which has them on it. Let us go down to a quick example of a graph. Here's a nice simple one. It has 5 vertices, denoted as V1, V2, V3, V4, and V5. It has 1, 2, 3, 4, 5, 6 edges. And there's a couple of other definitions which I've stored below us, which is we can talk about two vertices being adjacent. So in this graph, V1 is adjacent to V2. And V1, V2 is an edge that connects them. Furthermore, V1 is incident on V1, V2. So those are our terminologies. The last one is the degree of a node. The degree is the number of edges that are incident on that vertex. So an alternative way to say that would be it's the number of vertices adjacent to that vertex, assuming that you can't have multiple edges. We will disallow, for now, the ability to have potentially multiple edges connecting the same vertices. So we'll disallow that. Let's quickly denote the degrees. I'll do that in purple here. The degree of V1, well, there are 2 edges incident on it, so that's a degree of 2. V2 has a degree of 1, 2, 3, 4. V3 has a degree of 3. V4 has a degree of 1, and V5 has a degree of 2. Notice something. If we were to add these up, if we did 1 plus 4 plus 2 plus 2 plus 3, we get 5 plus 7 is 12. The important thing is that's an even number. We'll come back to that a little bit later. We'll have a proof that that is true, but that is a useful thing to observe. The last thing we want to mention for basic definitions is there are several ways you can store a graph. You could theoretically store it as sets, where you have a set of vertices and a set of edges, but that's not necessarily efficient for algorithms to process the graph. The two most common implementations of how we store the information is an adjacency matrix and an adjacency list. So, adjacency matrix stores the information in a bit of a funny way. I will add some information to this matrix. Each of these columns corresponds to a vertex, and each of these rows also corresponds to a vertex. And entries in this matrix, such as this entry here, tell us that there is an edge between V3 and V2. Notice that there's also an entry in V2, V3, this column and that row. That is because there is no directionality associated with these edges. It is possible that you have a directed graph where each edge has a directionality, like what I'm drawing in there. That is possible. We are not going to deal with that right now, though. So we will pretend like that's not the case. Now, with that in our minds, let us try and discover how much memory do we take to store this adjacency matrix. To store this, well, I need to have a column for every vertex and a row for every vertex. So this has a spatial complexity of n squared, if n is the number of vertices. Maybe we write that in a better way as the number of vertices squared. Now, let's look over here. For the adjacency lists, we have V1 stores a list. You could implement this as a linked list, as an array, whatever data structure you want to store a collection of those vertices. Whatever seems natural, you can do that. You could even implement that as a binary tree or a heap or whatever you wanted. We store a list for each of them. And again, if we were to add up the total number of things stored here, we would get that magical number 12. And that will actually turn out to be twice the number of edges. It may not be obvious to you at this point how these two things compare, but intuitively, let's think about it. Every single entry in this matrix, if there is an edge, must be a 1. However, this matrix sort of represents the upper bound for the number of possible edges we could have. The most number of edges we could have would be that we have a 1 in every single slot in this matrix. And that would correspond to having a bunch of lists of size 4 over here. No, so therefore, this adjacency matrix seems like it is going to be worse, but trying to categorize the maximum number of edges we can have, we will come back to later once we are analyzing this problem. Also notice there's some redundancy over here. Like I said before, these two highlighted entries are both representing the same idea. It's worth mentioning, the way that we index into this matrix is we can access it by using two different indices, I and j, and if it's a 1, we have a vertex, and if it's 0, we do not have a vertex. There are some nice mathematical properties of adjacency matrices that can be used that we will not really discuss in this class. If you take a class like linear algebra, you will likely discuss a lot about matrices and the operations you can perform on those matrices and the things they can tell you. Another related matrix to the one we have here is the Laplacian matrix. That tells you some more information about a graph. So there are useful things for the adjacency matrix, but it does tend to take more storage than an adjacency list. Therefore, for our purposes, we will almost always be using an adjacency list for our algorithms.